All right, so here we go. All right, so this is 6.1. It's the area between curves. So what we did with the integral before, if you watched the lecture on 5.5, was the area to the area under the curve was to the axes, right? Either to the x-axis or to the y-axis, depending on if you're doing the integration in terms of a dx or a dy, right? Today what we're going to do is actually we're going to take the area between two curves. And so I'm going to demonstrate that for you so you can understand this. So this first definition that we have here, right? It says that the area of the region bounded by the curves y is equal to f of x and y is equal to g of x, and the lines x equals a and x equals b, where f and g are continuous, and f of x is bigger than or equal to g. For all of the x's in the interval from a to b, we get this integral, right? So here's just a quick picture for you guys to understand, okay? Because it may make things easier for you to understand. So if I have a function, and let's say that this is my f of x function, okay? So if that's f of x, the way that we learned going from here's a to b, right? We learned that the area under the curve was simply this piece right here, right, to the axis. Agreed? Okay, so that's for if that was f of x, okay? If I gave you another function and I said it was something like this, right? And it went from that same a to b, then the area under the curve would be this piece, correct?
Yes.
Okay. What this new definition is telling us is this. If we take both functions from a to b, right? So it's closed off. It's a closed region. The area is going to be the area of f of x minus the area in g of x, and that will yield only this area. You can see that, right? That makes sense?
No.
Okay. That's all this section is. So when we do these problems, all we're going to be doing is really looking at either what function is above the other and then subtract them, or which one's further to the right and subtract it from the one on the left. Okay? So I'm going to take you through a journey of all of these problems today. So let's go to our first example. So if we look at this first example, it says find the area of the region enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. I did that already, right? I graphed it. Now what we need to do is we need to determine where the area is that is enclosed. And so we can see if we zoom in on this thing, there's an enclosure, right? And so that enclosure now needs to be the area that we're looking for. That's the area that we're looking for there. Right?
Yeah.
So it's this small area, but now we need to find the bounds that enclose this thing. And how do we find the bounds? What do we see the two functions do?
They overlap.
Well, they intersect.
Right.
And since they intersect, that means that the functions are equal to each other, and it looks like they're equal to each other at 2 points. So what we need to do is we're going to go x squared is equal to 2x minus x squared, right? And then from there, we're going to solve this thing to find out what the bounds are. This is just to find the bounds. So when we do this, I'm going to get 2x squared minus 2x is equal to 0. So then bringing out a 2x, this is what I'm going to get. So we can see that the bounds are going to be x is equal to 0 or x is equal to 1, right? Right?
Yes.
So then the integral is going to go from 0 to 1, and it's going to be the top function minus the bottom function. Well, which is the top function? It's the one that opens down, correct? The blue one. So the blue one is 2x minus x squared. Right? Because the negative in front of the square shows us that it's inverted. And so 2x minus x squared minus the function that's below. And the function below is x squared. And it's a dx integral, and the reason it's a dx integral, I should have talked about this already, but I blew it, is because the function's in terms of x, and so the cross-sectional slice is vertical. It goes up and down. I could have done it horizontally, but then my equations would have had to have been solved for y. And then it would have been a dy. It's easier in this case for me to go vertical, leave it in terms of x, and integrate. Don't worry, we're going to get into that more and more and more as we go. So then we can clean this up, right? We can say, okay, oopsie daisy, I don't want everything in red. So I'm going to get from 0 to 1, I'm going to pull out the 2. And I'm going to get x minus x squared dx, correct? And then when we integrate this, it's going to be 2 times x squared over 2 minus x cubed over 3 evaluated from 0 to 1. And that's going to give me 2 times 1/2 minus 1/3, right? So the common denominator is 6, so it's going to be, the answer is going to be 1/3. And since we're talking about area, what kind of units do we have?
Units squared.
Units squared. Clean that up a little bit because I don't want it to. I'm just going to highlight it. Here's my answer. Does that make sense? Pretty straightforward, correct?
Yes.
All right. Not too bad. That's good. All right. So let's go to the next one. And again, I graphed it for you already to save us some time. Here, hold on. Where is the area that's going to be shaded? Isn't it just this that's between here? Agreed?
Yes.
Okay. So again, what we need to do in this problem is find out when they are equal. Right? And we see that cosine is equal to 1 at 0 and at 2 pi, and 2 minus cosine is equal to 1 at 0 and 2 pi. Agreed? That's some trig that you guys should know. Okay, which function is on top?
2 minus cosine x.
It's the 2 minus cosine x. Now, here's something important for us to analyze and think about, okay? Which way should we integrate this? Should we integrate this in terms of y, or should we integrate this in terms of x?
in terms of y.
So if we did it in terms of y, we'd have to take a slice going this way, horizontally. But look what happens. If I go this way, am I hitting the same function?
No.
Am I hitting the same function going this way? Yes.
Oh, wait, yeah.
If I hit the same function, you can't do that. So right off the bat, by looking at this, going, all right, there's a slice, one little slice for me. Oops, can't do it that way. It's bad. So that tells me I have to go vertical slice. And if I go vertical slice, this vertical slice crosses which axis?
X-axis.
And because it crosses the x-axis, this is a dx integral, meaning everything must be in terms of x. See the thought process in working this problem out. It's all analysis. So we know that the bounds are from 0 to 2 pi. Very cool. We also, because of the slice, and I should write the slice down, because the slice is this way, we know this thing has to be a dx. So everything must be in terms of x. I think it was Daniel who told me that it was 2 minus cosine was the top function, correct? So then 2 minus cosine of x minus cosine of x, all taken times dx, right? Okay, so again, 0 to 2 pi, I'm going to pull out a 2 again, and I'm going to get 1 minus cosine of x dx. Any questions on what I'm doing so far?
What about the minus cosine x?
Yeah, what's minus cosine x minus cosine x? That's a minus 2, right? Cosine x.
Yeah.
So then I factored out the 2.
Oh, I see.
You're good?
Yeah, I'm good.
All right. Now from here, it's the integral of each piece. And since it's with respect to x, 1 is going to become what when I take the integral? What is the integral of 1?
X.
It's x. What is the integral of cosine?
Cosine. Sine.
It's sine. And now we need to evaluate this from 0 to 2 pi. Well, that's cool. We can see from here that we're going to get 2 times 2 pi minus 0, right? Because sine of 2 pi is 0. Right?
Yeah.
Minus 2 times 0 minus sine of 0 is also 0. And so we're going to get 2 times 2 pi is going to give us 4 pi units squared. We okay?
Actually, yes.
All right, good. Next. Now, in this definition, it tells us to take the absolute value, right? So if we have two functions and they alternate what they're doing, we're going to take the absolute value of their difference to be able to get the integral. Well, that's kind of funky. So instead of doing it that way, I treat this thing I always just go top to bottom, all right? When you use absolute value, people can get confused, and so instead of getting confused, just remember to do top minus bottom, okay? But you need to be able to find out where it's changing. And that's what we're going to do here. All right. So in this case, we have 4 equations given to us, right? Y is equal to 8 minus x squared. That's the one in black. Y is equal to x squared. That's in blue. X minus 3 is in like that lime green. And x equals 3 is that like forest green. Okay? But we see some transitions happening here, don't we? We see a transition right here at this value. It's going to switch blue being on top to blue being on the bottom. And then again, it's going to switch here, going from blue on the bottom to now blue being on top. Does that make sense? So we're going to have 3 different integrals to deal with this. Okay? Now, the integral of the whole thing, if you were to write it in absolute value, would have been from -3 to 3, absolute value of either function minus the other. Does that make sense? Because the absolute value is just going to find the vertical distance between the 2 functions. Or if they're horizontal, the horizontal distance between the 2. Is that clear?
Yes.
All right. So now let's look at this, the furthest left piece. So we're going from what value to what value? What is the lowest bound?
-3.
-3. Okay, where do they intersect? That's -3, that's -2, that's -1, that's 0, 1, 2. And this would be...
And so -2 and 2?
So this bound, though, this first bound that we're doing, is going to go from -3 to -2, right? Because the slice that we're doing here, again, has to be in terms of what?
X.
It has to be in terms of x. Because if we go in terms of y, what happens?
You're just taking like a chunk, right?
No,
You
look.
gotta do d of y.
D of y, what would happen? What's my red dot doing?
It'll hit the same graph.
Yeah, we can't have that. You must remember to analyze that to decide if it's an x or a y. Okay? All right. So, what function's on top in this first integral then?
Eight minus x squared.
In this region here, you're saying 8 minus x squared is on top?
Oh no. There's x squared.
X minus.
It's going to be x squared. Does that make sense to everyone?
I kind of don't get that because you're talking about the black line, right?
Well, I'm looking at this section right here. Right? So if I'm looking at this section right here, what's on top? Is it blue or black?
Oh, blue.
Blue. And blue is the x squared.
Got it. Yeah.
Right?
Get it. Yeah.
So then that tells me when I go back to this integral, I'm going x squared minus, and let's be careful, 8 minus x squared, this whole thing dx. Plus, now we want to do that middle chunk area, right? So where's that middle chunk going to go from what to what?
From -2 to 2.
That's it. From -2 to 2. Now what's on top?
8 minus x squared.
Minus x squared, right? Plus, what's my next integral?
From 2 to 3.
From 2 to 3. And now what's on top?
X squared.
So again, it's the same as the first one, right? Is everyone okay with this?
Yes.
All right, cool. And now we got to integrate all of this. Terrible. All right, so let's do this. We're going to get 2x squared minus 8 dx plus, what's that going to be? 8 minus 2x squared plus 2x squared minus 8 dx. Do you see how they change signs? Absolute value. Isn't that interesting? So now we integrate this. I'm going to get 2x cubed over 3 minus 8x from -3 to 2 plus 8x minus 2x cubed over 3 from -2 to 2 plus 2x cubed over 3 minus 8x evaluated from 2 to 3, and really I should put brackets so that we know what the bounds are doing, right? And you can verify me if you'd like, but the answer is 92 over 3 units squared. I promise I'm right. But you shouldn't trust me, right? I've told you that. Don't trust me, so verify. Boom. Isn't it pretty? All right, ready for another one?
Sure.
All right, time to throw a twist. So looking at this one, is it going to be a dx or a dy?
dy.
It has to be a dy. And I even put the red line there so you would see that it's a dy. Can you guys tell me why it cannot be a dx?
Because if it's vertical, it hits the same.
Perfect. Perfect. So if I were to do a vertical slice here, what happens? It hits itself. We can't have that. Okay? So now, instead of top and bottom, we need to be right minus left. Okay? So, what is the further right?
Y equals x minus 1.
That's correct. Now, I'm giving you the bounds in this one, but you can just set the two equations equal to each other and solve to get their value, right? Or you could use your graphing calculator and find their intersection points. For, is it x or for y's? That's an important idea. What are the bounds?
From -1 to 3.
-1 to 3. So that's 1, 2, 3, 4, 5. That's -1. 2, 3, 4, 5. Right? Because that's 0, 1, 2, 3, 4, 5. Now, if we start where you're -1, you're telling me, are we hitting all the way to here? Mm-mm. Remember, this is the area that we want shaded. Right? This is the region that we're looking for. So what are the bounds going to be? So -3 to 5. Okay. Now, if we go -3 to 5, like you just told me, would that make sense if we're talking about dy?
Oh. It's with the. Oh, I see.
So it's -2 to 4.
There you go. What
Yeah.
the variable is, yes, what the variable is, is what dictates what the bounds are going to be.
Oh.
Could you say that again?
Sure.
Yeah, repeat it one more time.
Yeah, since we are talking about dy, right? We established that. That was the very first thing. Our bounds must be with respect to y. The ones that we did prior were all dx, so we only talked about dx. And when we only talked about dx, you only gave me x values for the bounds. Well, to get you to really think, I finally went to a dy example, and what did you give me? You gave me x bounds. X bounds don't work with dy. Dy dictates that we must use y values for our bounds. So the y values for the bounds are going to be here at -2 up to here at 4. I even try to give you a hint, pointing them out that it was from -2 to 4 because I thought that it would make you stumble. Turns out I've got a little bit of experience teaching this, don't I? So the bounds must be from -2 to 4. And Ray was very, very excited that he got it. Does that make sense to everyone? Is there any questions or is there any ambiguity in what I'm saying? We're good? All right. Now we have to decide, since we're going to be in dy, what's our function got to be in?
In terms of y?
That's it. Everything must be in terms of y. So now the equations that we have must be in terms of y. So you told me, Daniel, that the further right function was y is equal to x minus 1. That's correct. But we need to write it now in terms of y. So what would it be?
X equals y plus 1?
So it's y plus 1.
Oh, yeah.
Right? Because you solved it for x, right? In the previous examples, we had y is equal to something. We didn't write the y part. We only wrote the x part. So in this case, since we're in dy, we only write the y part, which is y plus 1. That is the top, or let's say the right function, minus the further left function. And what's the further left function?
Oh, well, y squared equals. Oh, would it be when you take like the square root? Like, because it's the parabola, but would you just would you write it like that, or would it be just like the square root of 2x plus 6?
Remember, we want our equation to be in terms of y. What you're doing right now is solving it for x's. You're putting everything in terms of x.
Okay.
Y squared.
So, okay, let's play. Y squared is equal to 2x plus 1. How do I solve for x, my friends?
You bring it, like, you isolate it.
Okay, so tell me what to do.
So subtract 6 and then divide by
Wonderful.
2.
We're going back to algebra 1. Now what?
Divide by 2.
Wonderful. So I'm going to get 1/2 y squared minus 3 is my x. Agreed?
Mhm.
So that's the function I'm going to plug in. 1/2 y squared minus 3. And then the whole thing is dy. So when we go to dy, not only do our bounds have to be in respect to y, our functions have to be in respect to y. Does that make sense?
Yeah.
And I said it early, but you probably didn't pick up on it. First example, I'm like, we could have done this in dy, but then we would have had to change the equations that we were given, right? I kind of just quickly said it. When you watch the video again, or if you watch the video again, you're going to be like, oh, dude, he set us up from the beginning. And I was. Okay, so now from here, we can do this, right? No problem. So let's combine things so it looks pretty first, because we're all about that pretty life. So I'm going to get a negative 1/2 y squared plus y plus 4 dy. Agreed?
Agreed.
Okay. And now we can take the integral of this. Ain't no thing. 1/2 times y cubed over 3 plus y squared over 2 plus 4y. That whole thing evaluated from negative 2 to 4. Right? And we can clean that up just a bit. 1/6 y cubed plus 1/2 y squared plus 4y. This thing evaluated from negative 2 to 4. And then we plug in, right? Do you guys want me to do all the plug-in stuff, or can you guys do it from there?
Do it from there. But you like, or don't give us an answer. You have to like a second to like solve it.
Oh, sure. I'll give you a second. Try and see if you can solve it from there, that evaluation. I like the way Ray's doing it. He's going straight to the calculator. You know, in the calculator, what you could do, Ray, from right here, you could plug in like I showed you. Just call these all x's, and you could find the area under the curve of this function.
I don't know how to do that.
I taught you.
I don't remember. Wait. Oh, yes, I do. Okay. Give me a sec. By the time I figure this out, I feel like.
Well, do it manually, and then I'll talk about that again.
Okay.
I'll talk about it at the end of class, so you guys can double check your work.
There's, jeez.
Yeah, got 14 over 3.
There's a way. Screw this calculator.
Could you show us, like, because this goes back to fundamental theorem, right? Where you do them, like, you plug in the f of b minus f of a, right?
Okay, here we go.
Okay, I'm scared.
Agreed?
That's exactly what I did, and I still got it wrong.
Mm-hmm. Same. So maybe it's not exactly what I did. But yeah, it makes sense.
Oh, I think I messed up on the signs, though.
Do we agree?
Mm-hmm.
I still get 6. I don't know what I'm doing wrong.
Do you agree?
Sure. Okay. Oh, damn it.
I got it now.
That's good.
I
Good.
forgot to bring the negative over.
Yeah.
Second part, and I got 6.
Yeah. Hey, look, the calculus isn't the hard part. It's the algebra and arithmetic that eat us up.
Yeah.
Nope. They do be.
All right.
Redeem ourselves.
Oh, yes, Ray, you don't want me to move.
Yes.
Oh, got you. I saw the move.
Can you go to the original problem real quick? Sorry. Okay, we're good. Thank you.
All right, here I'm gonna give you guys one for you to try. I even gave you the cross-sectional slice. So what's it in terms of?
In terms of X.
All right, so it's a dx. All right, you guys try it. I'm gonna sit and laugh.
Reassuring.
Well, I want to see you guys concentrating and see how it goes. I firmly believe in you guys. Did you get it, Daniel? What happened?
I just like don't really know it, but it's like I see the bounds, but it's like just like confused at like where to start.
How to find the bounds?
Like, because I'm not so it's like 'cause I don't know if I'm doing like 2 integrals or like the 3, like because we have like the different examples.
Well, how many areas are shaded?
Oh, just 2.
Just one. The area that's the enclosure.
Oh, it's just it's like the between the blue and the red.
Yep.
Okay.
Yeah. Hold on one second. I gotta stop sharing for a second.